Greetings! In this video I'll be solving this another integral, again using QSUB, and it turns out that this one is not so hard, although it might seem confusing, but quite nice QSUB can be used, which is to some might seem surprising. Alright, so one would maybe try doing some trigonometric substitution or inverse geometric function substitution or something like that, but indeed it's possible to solve this in a different way. And there's more ways to solve this. I can actually choose more variants of u. I might actually show both variants. So let's say in the first case I will say that u is this inner part of the square root x squared plus 1. In such case I will have x cubed still times the square root of u, and then du will be 1 over 2 times 1 over 2 times, oh actually in this case it's not yet, that's way, du will be just 2x dx, and that means that, make this a little more nice, 2x dx, and that means that dx will be du over 2x. I'll be able to replace the dx by du over 2x. Alright, so this simplifies the x cubed a little bit. It makes it fall down to x squared only. So x squared times u to the 1/2 power du, and the x cancels out, and this 1/2 goes here in front. And now also I can further work and play with this u actually. So this is nicer than one might have expected. One might have expected some trigonometric functions or something like that, substitution with complicated stuff. But instead what I can do is I can further play with what I set u to be. I set u is x squared plus 1, but I can also say that x squared is, I'll use algebra, u minus 1. X squared is u minus 1 as I say here. That means that this x squared can be replaced by u minus 1. U minus 1 instead of the x squared right here. And what that means is I have suddenly 1/2, and I can multiply this out, times the integral u to the 3/2 minus u to the 1/2 du. Now, this is nice, and maybe we'll go a little bit to the left because we've run out of space a bit. The point now is I can just further integrate this the normal way. This ends up being u to the 5/2 over 5 over 2, all this in the parentheses, minus u to the 3/2 over 3 over 2 way plus c, of course. And what this is, well, over 5/2 like this, so it's 2 over 5 times 1/2, just to do it slowly and not mistakenly. So 1 over 2 times 2 over 5, like this, u to the 5/2, minus 2 over, just to make it, maybe do it, 2 over 6 times u to the 3/2 plus c, and then just substitute back what u was, and indeed this can be verified as correct result. I had set u to be equal to x squared plus 1, so x squared plus 1 to the 5/2 power. Of course one can play with the roots and put this parentheses to the 5th power inside the root, but instead I can just write it this way. Again, x squared plus 1, just replacing q by what I had set it to be. Not using this x squared equals to u minus 1, but still explicitly the u itself, to the 3/2 plus c. And this indeed is the correct answer. And the interesting thing about all of this, and I will probably use a small piece of paper here to delete this previous instance of calculation, is that I can do this same thing, but even change the u. I can choose the u to be something even different. So it's possible. So namely, what I can do is, again, I have this integral, x cubed times square root of s squared plus 1 dx. But now I will say this entire square root is u. So s squared plus 1 in the square root is equal to u. Therefore, if I do du over dx, I get this classical 1 over 2 times the square root via chain rule, and via chain rule also 2x in the top, like this. Now, these 2's cancel out, so in simplified manner I get x over square root of x squared plus 1, and dx will equal, just switching all of this will be du times x squared plus 1 over x, like this. Now I can replace the dx by this entire expression for what dx is equal to, namely this. X cubed, I will just keep it the way I had. Then u is still this, because I set u to be this entire square in this case. And the dx will be this s squared plus 1 over x du, as follows. Alright? X squared plus 1 in the square root over x. Nice. And now because I know that this is u, I can say this is u as a whole. So this is u. Then again, this makes it just x to the second power. Alright? So what I have nicely left is this x squared u squared du. But I know that u squared should be equal to something. And I said u equal to square root of x squared plus 1. That means that I can just take both sides to the second power. U squared equals x squared plus 1. And x squared will equal, and this is a little bit of a mess, so just to break it down like here, hopefully it will be at least the least bit visible. U squared minus 1 equals x to the second power, right? So u squared minus 1 can replace this x squared. So I have this integral u squared minus 1 times u squared du. Alright, so what this brings is finally this integral of u to the fourth minus u to the second du, which is u to the fifth over 5 minus u to the third over 3 plus c, but of course I have to replace u by what it namely should be. And now if I plug in these roots inside, well, this gets a little bit complicated because it's to the, if I put this here, this is x squared plus 1, this is equal to x squared plus 1 to the 1/2 power, alright? And then if I plug it in for the u, I won't do it because there's no more space, but you see that it ended up as the same result like before. It ended up like x squared plus 1 to the 5/2 over 5 or 1/5, x squared plus 1 in parentheses to the 5/2 minus again x squared plus 1 in parentheses to the 3/2 times 1/3 plus c. So this indeed is the same result as was yielded before.